With drag comes terminal velocity. You might have heard this word before. What's terminal velocity? It's the speed you go when drag is the only thing that is slowing you down. Most often, we think about this in with respect to something that is, skydiving out of a plane, for example. So you have one person skydiving uh, without a parachute for some reason, and one person skydiving with a parachute. You know, we expect the person with the parachute will end up going a slower speed the whole way down, basically. And the person without the parachute will be speeding up at first, but then they will reach a speed that will be constant the whole way down because of the drag that is running up against them. Now, that speed that they reach, the parachutist is also reaching a constant speed, but the constant speed of the person without the parachute will be much larger, probably, than the person with the parachute. So let's examine this a bit at a time. Let's say that you are in a very high hot air balloon, and you jump out. You're gonna be fine. There's a marshmallow at the bottom. It'll catch you. Here's a marshmallow, very soft. Okay. Oops. Well, looks like you're not gonna land on the marshmallow. You'll be fine. Don't worry about it. So when you first jump out of the plane, the only force that's affecting you, it's a balloon, not a plane. Don't worry about that either, is weight, right? Because you don't have any speed yet. Your speed is still zero because you just stepped off. So if weight is the only force and your net force is downward, then you're going to speed up downward. So if we look a little bit later, you're down here. This is V1. This will be 2. You do have a little bit of speed now. And so you're picking up speed, you're picking up some drag, but at this point, the drag is still lower in magnitude than your speed. Well, if there's a net force downward, your acceleration is still pointing downward. Acceleration and velocity are both pointing downward, the same direction. You're going to speed up downward. So if you're speeding up downward, you're going to keep going that way until we get to a situation like this, where your weight and your drag are finally at the same point. Your drag has sped up to the point, or your drag has increased to the point because you have sped up, where it's balancing out the weight. And your drag is not going to increase anymore because then you'd have to speed up more. But you're not going to speed up more because your net force is zero now. So in order for that to happen, your weight has to equal your drag. And we can set both of these equal to the equations that govern them. So we know the equation for weight is mg. We know the equation for drag is up here with all those terms. So we have 1/2 CD rho A and V squared. But this V is specifically the terminal speed. It would be best if this whole thing was called terminal speed, because this is the magnitude of the velocity, but history has stuck with this term, so it's fine. This is what we want to solve for. There's just some algebra. There's a lot of terms in this algebra, but it's just some algebra to solve for this. So we'll do VT squared is equal to multiply, divide 2mg over CD rho A. Final step, take the square root. We're solving for a magnitude here, so when we take the square root, we do not need to put a plus or minus out front. So this is our expression for the terminal velocity for something that is only falling. And you can see that there's some terms that should make sense here. It depends on the mass of the object. So a heavier object, or I should say a more massive object, you would expect to have a higher terminal velocity. More gravity would have a higher terminal velocity. So if you went to a different planet that had a higher gravitational acceleration. The coefficient of coefficient of drag. So something that is less aerodynamic would have a larger CD, therefore a smaller terminal velocity. Rho is on the bottom as well. So if the gas is denser, then you have a smaller terminal velocity. And the cross-sectional area is on the bottom. So something that has a larger cross-sectional area is going to have a smaller terminal velocity as well. And in fact, this is the whole point of parachutes, right? So if you have a larger cross-section to your parachute, if you have something that's more like 10 meters squared, then you're going to slow down your terminal velocity by a great deal compared to just U. Also, to a smaller degree, CD is going to change, right? Because this is a concave surface as opposed to just U, right? So CD will change, but we're not really dealing with CD in this class. So let's estimate a little bit. So we're going to estimate some values to plug in for the terminal velocity of this person over here. So we'll just plug in some values. So let's estimate the values for a person. What's the mass of a person? Obviously, the masses vary. We'll just put in 80 kilograms. We're still going to use CD as 1/2, although that could vary. Rho is for the air. Obviously, the air is going to get less dense as you go higher in elevation, but we're still going to use the same value. The area is the thing that we need to calculate. People tend to be, if you draw a person, right? They tend to be just a little under 2 meters high. So that would be 2 meters, right? And they're a little under, about 2/3 of a meter, give or take. So if we went with 2/3 of a meter, if we went with underestimating this down to 1/2 and overestimating that to 2, we would get a cross-sectional area of about 1 meter squared. Right. And I'm using the flattened cross-section here because that's the direction that person is going there. So we'll use about 1 meter squared for the cross-sectional area. And let's just calculate our terminal velocity. So we have 2 times 80.0 kilograms times 9.80 meters per second squared divided by 1/2 times 1.2 kilograms per meter cubed times 1 meter squared. I get 51.1 meters per second. That is pretty fast. So if you were to convert that into miles per hour, so 51.1 meters per second in miles per hour. I'll just Google that real fast. It's 114 miles per hour, which is probably faster than you would like. Especially, We'll just put a marshmallow over here too. There's a marshmallow. Yay.